Thank you, Magdalena, and thanks for everyone to everyone for being here. It's yeah, I don't know. I like the Newton Institute, and I'm glad to see a lot of you here and a lot of new people. So I guess I'm giving an introduction to chromatic homotopy theory, and chromatic homotopy theory has been around for a while. So I think I planned lots of different versions of this talk, and now some sort of combination of all of that will come out, and we'll see. You know, if you have any orders for things for me to talk about next time, let me know. So maybe the beginnings of chromatic homotopy theory have to do with mu, as you know, as we've seen, mu has been playing a role in a number of talks, and the reason is that as Marcus explained, this complex coordinate spectrum has another sort of role that it plays, and its coefficients classify formal group laws. So formal group laws are, well, how does this go? It has to do with the fact that if you have a complex orientation, then it equips E with a theory of Chern classes, and so then you tensor two line bundles and try to figure out what the Chern class is for the tensor of two line bundles, and that the rule that tells you how to compute that in terms of the Chern classes of the original line bundles is a formal group law. All right, so then why does this sort of lead us to this thing we call chromatic homotopy theories? Because these formal group laws are some kind of algebraic objects, so in characteristic P, they are classified by height. That's an invariant, let's say H or N, some number between 0 and infinity, including infinity. So what is the height? Well, I don't want to get into sort of writing out formulas for formal group laws, but I just want to write something. So we said, okay, you know, a formal group law is a thing that tells you how to find out what the Chern class is for a tensor product of line bundles. So suppose you take the pth power of a given line bundle, then you have sort of a multiplication by p map in the formal group law. So let's say this is usually denoted by that. And this can be expressed as a power series, and that power series might have the form where there's some coefficient times x to the p to the h plus higher terms. And so if this coefficient here is invertible, is a unit, then our formal group law has height h. And so that's a complete invariant over over algebraically closed fields, and it leads to a thing that's called the height filtration. And so the sort of the mirror of what happens in homotopy theory that reflects this filtration, that's what chromatic theory, chromatic homotopy is all about. So maybe a bit more specifically than that, let's put it this way. So mu here gives rise to the Adams-Novikov spectral sequence. And maybe since, look, I said in characteristic P, and now this P is going to be fixed somewhere, so here, everywhere, we fix a prime P. First thing we do, so instead of MU, we could work with a P localization, which has this someone that splits off, that's not this geometric, but it's more efficient. So BP, the Brown-Peterson spectrum. And then in this sort of P primary world, this height filtration, well, first algebraically was used to construct the chromatic spectral sequence. Maybe let's see here. So this stuff here is Quillen. Over here we have Miller, Ravenel, and Wilson constructed this spectral sequence. And that's a spectral sequence that computes the Adams-Novikov E2 page. And so the observation here that Miller, Ravenel, Wilson made is that, okay, well, you were trying to compute, say, homotopy groups of spheres. They're super complicated. We have this Adams-Novikov spectral sequence. Well, that's sort of not as complicated, but it has certain nice properties, and it's kind of still pretty wild. But then you sort of deconstruct it into this, into something that has nice periodic structures and periodic families, and so you sort of run this kind of white noise or light or whatever you want to, however you want to look at that, through a prism that deconstructs the chaos into wavelengths, and you have you can see patterns now. Okay. All right, so that's all kind of stuff from the 70s. And then, yeah, so that's kind of where it all starts. I don't know. It's the point, well, I don't know. So then, I guess I wasn't around then, but I'm imagining that all of this was the inspiration for Ravenel to write this amazing paper from, I guess, published in 1984, what it's called Localization with Respect to Certain Periodic Homology Theories, in which he lays out sort of like a vision of the topological counterpart of where is this stuff coming from, and so that sort of kicked off a new period in this area of math. I don't know. So I guess that's the algebraic stuff, and then sort of like in fact there's a maybe has topological homotopical origins. So then we need to introduce some sort of new notation. Well, by new I mean like stuff that's not here. One of those key players, those periodic homology theories, is this Morava K theory. I'm gonna keep switching between H and N, I think, and that's fine because they kind of look almost the same. So let's say Kn, Morava E theory. So it's a complex-oriented spectrum. there's various choices to be made here. The coefficients, for example, could be taken to be say, run series polynomials on a single variable, this Vn, the same as this one. So it's made invertible. So indeed, this comes with a formal group law that's coming from the orientation. And the usual choice of a formal group law here is a thing that's called the Honda formal group law. And if we stick an FP bar here, then we don't have to worry so much about the choice. But we could put in any other fields here. I don't, between FP and FP bar. So its P series, let's call this Fn, is literally Vn times P to the n. There's no higher terms. Okay, so what are some examples? Well, V0, we're thinking of V0 as P. So so in K0 we sort of have FP and then adjoin P and invert it. So so really that's maybe a convention, right? So K0, we just think of that as HQ. K1 is just L, where this is the Adams L summand. Of Ku, so it's a piece of complex K theory, not P, and so on. So these Morava K theories are okay. Well, they play various roles, but one of the roles that they play is that we get to localize with them, and then our life gets a little bit simpler and more concrete. So we take a category of spectra, and we look at these localizations. So let's pass through localization with respect to Kn. And then another one that combines these is Ln, which is localization with respect to, let's say, just because I haven't introduced any other things, I write it this way. So we can localize with respect to the wedge of the first n+1 Morava K theories. And all right, so then there's this cool theorem, chromatic convergence. To Hopkins and Ravenel. That says that, well, okay, the P local sphere is equivalent to the homotopy limit of these Ln localizations of the sphere. Okay, so the consequence of this is that if we want to understand, say, the sphere, maybe one approach would be to study its Ln localizations and then see how they patch together. And then the other, well, then you say, well, how do I study these localizations? And, well, one way to do that would be to look at these fracture square. Well, let's say they inductively build Ln from ln minus 1 and the kn localization. And they're glued along the n minus 1 localization of the kn localization, so this is a pullback square. Okay. So this maybe it seems really simple the way I'm presenting it. However, sort of understanding how these squares, sort of, the gluing information here is not all that simple, and is the subject of the chromatic splitting conjecture. Which, as far as I know, is I don't know, maybe one of the hardest things in chromatic homotopy theory. So I don't know anything about it beyond n equals 2. So Agnès Baudry has disproved a strong version of this conjecture, whatever it is. The splitting conjecture is about sort of saying that this, but there being a splitting here, so that gluing information is as simple as it can be. But yeah, so it's sort of like the strongest possible version fails at the prime 2 at height 2. However, there is a good explanation for that failure, and there's some sort of it's still possibly quite true in general in that weaker form. All right. What questions do you have at this point? Well, let me know as they start surfacing. So the upshot of all this is that maybe you want to study Kn local homotopy theory, or Kn local sphere, or Kn local spectra. And so how do we do that? So I think maybe this was sort of stuff from the 80s. Now we move into the 90s. So we talked about this Kn and its formal group law. So it's some formal group law in characteristic P. It's a very nice or simple sort of thing. So now, but okay, well, now a detour back to the 60s, I guess, is the fact that formal group laws have behaved functor of deformations to sort of characteristic, to P-complete rings. So if I take a formal group law in characteristic P, then I could look at ways that I can lift that to some P torsion or P complete ring, well, that actually defines a functor of deformations that was studied by Lubin and Tate, and the functor is representable. So the situation is that if you have some formal group law F over a field K, then associated to that is a ring, like P complete. K, the characteristic of K is P, and maybe K is perfect. standard conditions. So then the conclusion is that there is a p-complete ring that carries a universal deformation of that ring. Okay. So that's due to Lugan and Tate, but then, in fact, Morse, Hopkins, and Miller upgraded this result to homotopy theories. In fact, they associate to such a pair an E-infinity ring spectrum called Morava E theory. So this assignment has a couple of great properties. One is that, well, this ring is in fact K of the height of F local. And maybe more importantly, definitely more importantly, this is a functorial assignment. Okay? And what that means, or what that buys us, is that it puts us in a situation where the functoriality tells us that the automorphism group of gamma, K, and gamma is F, acts on this Morava E theory via E-infinity ring maps. Okay, so now I get to justify my presence here. Okay, there's a group acting on something, so we're Equivariant. Any questions? This group is generally not trivial. In fact, this is a nice pro-finite group. So let's look at some examples of what it is. Maybe first I will introduce this notation that sort of is a shortcut here. You know, I want to emphasize that E is a functor, but then maybe I mentioned before that this sort of the height is a complete invariant of so you know, over a algebraically closed field of characteristic P, there's going to be a unique formal group law of that height. So I can just choose one. So for example, if we choose the Honda, so let's do this notation, that I'm not going to be very strictly following, then at some point it's important to go back to this functoriality, but for now, let's just do this and say En, that's our shortcut notation, that's going to be E of the Honda formal group law of height N, and the field is Fp to the N. And even though my formal group law is defined over Fp, it's good to adjoin some roots of unity to the field in order to sort of realize all the automorphisms. All right, so this is maybe a more standard sort of a single ring spectrum that you can call the Morava E theory at height N. Okay, so for example, when n is 1, this E1 is equivalent to the P completion of the complex K-theory spectrum. And now another notation, then the automorphism group of this pair often goes by the name Gn. And this is called the Morava stabilizer group. So when n is 1, this G1 is the p-adic units, and it acts on P-completed K-theory by Adams operations. Okay, when n equals 2, we have E2. Well, this is closely related to some versions of topological modular forms. So now it's my turn to tell you previews of what other people are going to talk about. I have no idea. So anyway, topological modular forms are going to appear in Leonard's and Folling's talk. So perhaps not exactly the relationship to E2. Okay. So why do we like this En? Is because it's a, unlike the sphere, it's a very easy to understand spectrum. So, so in general, so E, well, the homotopy groups, so it's an even periodic ring spectrum, and it's homotopy, so pi 0 of E is this Lubin-Tate ring that classifies the universal deformation. And then there is a sort of, and it's even periodic, okay? So there's some U in degree 2 or minus 2, depending on how you do that. So the Lubin-Tate ring itself, well, it's also a very nice ring. So it's non-canonically isomorphic to sort of an extension of a Natal extension of the p-adic integers, joining some roots of unity. And then there's some power series variables that are the deformation parameters, so U1, U2, up to UN minus 1. Okay. And these U's are all related to the V's in the Morava K theory. And this one's related to Vn. Anyway, so this is a really nice ring. Okay. All right, so we can study easy, nice rings, but another reason why we like this particular one is because it helps us understand the Kn local sphere, in fact, Kn local spectrum more generally. So theorem, like I should put a bunch of names here. I mean, in this version is Leibniz and Hopkins, but probably worthwhile also saying this is due to Morava, because I guess he had a sense for this before there was the technology to make it precise. But the Kn local sphere is equivalent to the homotopy fixed points in a sort of continuous homotopy fixed points for this profinite group action on En. And in fact, I guess John Rognes interpreted the sort of maybe the details that go into showing this in the Devnitz-Hopkins work as saying that, in fact, this is a pro-Galois extension, so a pro-finite Galois extension, K and local, for, with Galois group Gn. And even better, the sort of this En, the specific En, not quite, but then the sort of something very close to it is the algebraic closure of the K-n local sphere due to I guess work of Birgit Richter and Andy Baker. And what I mean by almost is really like, okay, we need E associated to some high n formal group law over FP, so that all these Galois automorphisms are in there. So sort of take the Galois closure of this EP again. Okay. And then a newer sort of points of view on Morava E theory further sort of justify this point of view that En is a really nice sort of algebraically closed ring or like field, an analog of an algebraically closed field in K-n local and in fact T-n local homotopy theory. So so maybe that's the preview. 21st century chromatic homotopy theory that this is E for whatever formal group law over an algebraically closed field is sort of algebraically closed in the sense of sort of chromatic Nullstellensatz. This is due to Berthman, Schlank, and Ewan. Okay, any questions? I don't even need to erase. Yes. Okay, so there's there's sort of the Galois-ness of this extension. In fact, makes it stronger than what I've just said. So in fact, okay, well, P is already fixed. So let's not get confused about that. The category of K-n local spectra is itself sort of recovered by descent from K-n local E n modulus. So once we write something like this, say descent, the implications for what this means or the reasons why it's true are already present in the Devnitz-Hopkins paper, the sort of working towards writing it in this particular way involves more recent work. Maybe one way of thinking about this is through work of Matthew on Galois, categorical Galois correspondence in this kind of world of infinity categories. And then sort of using, maybe more recently, sort of using pro-Etal topologies and things like that. Itamar Moore has sort of expressed this in this more kind of modern technology of dealing with profinite groups. Anyway, I'm sure there's lots of other names and lots of different perspectives on this particular thing. So the upshot here is that if you have any KN local spectrum, you get to recover it from its EN homology along with the stabilizer action, and sort of the computational implications were already there in the 90s. Okay. So, let's see. Okay, does anyone have any questions? So let's see. Okay, so what have I done so far? I just said, okay, we want to understand, I don't know, spectra or the sphere spectrum. And we should do that by looking at KN localizations. To study KN local things, in fact, we should look at EN modules with an action by the stabilizer group, and so we have to sort of understand how do we deal with taking homotopy fixed points. So
I have a question.
yes.
What does mod KN EN mean? What category is that?
So this is KN local EN modules. So I'm told I'm supposed to call this the Ninja Turtles category. Because I don't know. For a certain, because it sounds like it's a KN local EN modules. I don't know. I don't remember. Not my joke. I don't know. But anyway, I guess I also hear that the Ninja Turtles have come up. Whatever. There's a comeback of the Ninja Turtles in the last few years or something like this. So maybe this is not such a dated thing where you know exactly how old you are, but if you understand this too. All right. Very good. Okay. So, all right. Any other questions? Yes. Yes. So here, well, if we need to complete, we do that. So one way is EN smash X, and then KN localize if needed, but so that we land there. And then the other way, just take homotopy fixed points. An object here is a thing that has a GN action. Okay. So anything else? Okay, so the big question is like, okay, how do we understand? So somehow we've reduced everything to understanding homotopy fixed points for this profinite group, and I'm claiming it's a very nice group, but how do we understand homotopy fixed points, these continuous homotopy fixed points for these for the group GN? And the short answer is hard. Okay, when n is 1, we've seen that, so G1 is ZP cross. Okay, so when P is odd, this is a topologically cyclic group. Let's just write it for you know, the K1 local sphere. So it's E and H, or E1, H ZP cross. Because this is topologically cyclic, generated by a single element, we can write this homotopy fixed point thing as just a fiber sequence. So where if L is a topological generator there of ZP cross, we just equalize the action of that generator. So this is, I mean, this is the same thing as taking the Z homotopy fixed points. I guess this is due to Baird and Ravenel, I'm not sure. But perhaps it's written in a paper of Rousfield, maybe? I don't know, or someone else. I don't remember.
Rousfield cites Adams, Baird, and Ravenel.
Adams, okay, thank you. Okay, thank you. So this is kind of nice and easy, but already when we look at n equals 2, the situation is quite a bit more complicated. When n equals 2, I guess, well, here's an example. Well, okay, actually, you know what? I wanted to write also P is 2. If P is 2, then the following thing happens. The ZP cross is no longer topologically cyclic. So we have C2, that's, you know, the plus minus 1 inside of Z2 cross. The homotopy fixed points for that action is KO. So I'm going to write this as E1 HC2, but this is the two completed KO real K theory. And now we still have this resolution, but now, I wrote KO. Sorry. But now we have these sort of homotopy fixed points with respect to a finite subgroup playing a role as well. Okay. If n is 2, I guess things get more hairy, and I will just tell you that there's the work of Boris and Mahold and Resk that say at p equals 3, for example, where they write down the K2 local sphere in terms of, so there's a resolution of the K2 local sphere in terms of finite certain finite subgroups of the Morava stabilizer group G2, and the resolution is of length 4, where we start, you know, this is in 0, 1, 2, 3, 4, okay? Okay, so what is 4? 4 is 2 squared, the height squared, okay? So this is, in fact, the beginning of a sort of a pattern. And what is the pattern? Is that It's the same kind of idea that if you're trying to understand the cohomology of these profinite groups like Gn, so Gn is a virtually, it has finite virtual cohomological dimension. So it has virtual cohomological dimension, that's n squared. So that means that it has an open subgroup of actual dimension n squared, and some finite subgroups that may cause sort of infinite dimensional phenomena. But other than that, it's a nice finite dimensional group. Okay, so if you were to study the cohomology of such groups, then you have sort of one strategy is to split up your problem into using these kind of finite resolutions in terms of the finite subgroups. So finite meaning perhaps length n squared, resolutions in terms of the finite subgroups. And then, so when it comes to resolutions of the Kn local sphere, resolved in terms of E and HF. Okay. And then, then you want to also understand E and HF for the various finite subgroups. But now we are dealing with just simple, rather simple situation because we have a finite subgroup, and now I'm going to tell you the finite subgroups are not all that complicated. Okay. Any questions while I erase? All right, so maybe I'll just say very briefly because I have many more pages of notes than I have time today, but thankfully I'm speaking again next time on Thursday. The finite subgroups that appear completely classified, maybe the most interesting ones, or the ones that will cause you the most trouble, are the sort of P subgroups there, because we are P completed, in particular in this Kn local situation. So the sort of finite P subgroups are, either cyclic of P power order, or when P equals 2, in very special cases, Q8. So these are rare. Okay, this is a quaternion group and doesn't appear very often as these subgroups. So, the groups that Jeremy were mentioning are sort of, Jeremy was talking about sort of, here are some really, simple groups you might be interested in. And so maybe one way of thinking about like how would you get such a restricted set of groups is by looking at subgroups of the Morava stabilizer group. Okay, so Okay, so now let's see. Okay, so I'm going to soon switch to p equals 2. I don't know if I should already do that now, but maybe let's wait a second. So well, I don't know. Maybe we can switch to p equals 2. So when p equals 2, one of these subgroups is a C2 inside of the stabilizer group. And it's exactly the sort of the plus minus 1 that corresponds, at height 1 to the complex conjugation. And there's a sort of a certain involution of every formal group law that will be that. So this group is in fact compatible with complex conjugation in that so the theorem of Jeremy Han and Danny Shi is that there's in fact an orientation from this MUR, so the C2 spectrum, the C2 equivariant orientation to E and for any n. And so this makes the En sort of higher height analogs of Kr as well, not just of Ku. This orientation is, I guess, relating this sort of algebraic sort of point of view on ENs through this formal group laws to the geometric point of view on MUR. So another consequence of this orientation is the fact that it gives us even more structure. So now suppose, well, okay, let's do just a little bit of sort of a I don't know, reminder from and the point of view that Jeremy was talking about last time was that we maybe really are interested in these Borel style spectra like En. So it's just a spectrum with the G action. In this case, we're looking at some finite group actions. But that's okay. We should also it's useful to look at it as a genuine equivariant spectrum because of that. So it's a Borel, and sort of that is enough for us to put it in this world of genuine G spectrum, or let's say F. But then, in fact, we also talked about the En being an E infinity ring spectrum. So then this kind of incredible work of Blomberg and Hill tells us that we can, that means that we have this sort of fancy norm structures in En. So that it's in fact sort of genuine E infinity, or I don't know what you call it, genuine commutative infinity, or an infinity multiplicative structure. What that lets us do is lets us sort of norm up or norm. We have norm maps, so we don't have to sort of only multiply along finite sets, but we can multiply along finite G sets. So what that gives in particular here is, you know, if C2 is a subgroup of the finite group F, then there's this sort of NUR normed up to F. Maybe I should just write that. To F, that this is an object that, a kind of object that features prominently in the Hill-Hopkins-Ravenel work on the Equivariant variant problem. And so the C2 orientation then gives an F equivariant orientation of En. Because, well, we norm up and then we multiply using this fancy multiplicative structure. And so what else I wanted to say today is that I wanted to sort of tell you about a sort of recent work of Leonard Meyer, Danny Shi, and Minghong Zheng on sort of understanding the differentials and the spectral sequence, computing the homotopy fixed points or some related thing of these spectra E and HF for general N's and F's, or somewhat general at the prime 2. But maybe I'll save some of that for next time. And right here. Thank you.
Thank you. Any questions? Come on, people.
Question.
Yes.
So, what about this genuine irregular decommutative structure of En?
How do you use that?
How do you make it?
Oh, how do you make it? Mike, are you going to talk about that?
Yes.
Thank you. All right.
Any different question for later? Yes. Any other questions? Okay. If not, then let's thank Vesna again.